Good morning, everyone. Today, I'm going to talk about innovations in fertilizer use, and I hope to convince you that we need to do a better job of fertilizing in order to raise high maize yield. Now, I come from Illinois in the United States. Illinois is right in the middle of the main U.S. Corn Belt region. This is where I live, and this is where I do my research. So I have a close-up of Illinois showing you where I do my research. Now, the University of Illinois is in Champaign, but we also have research sites in the northern part of the state and in the southern part of the state. And Illinois is a long state from the north to the south, 630 kilometers from north to south. And it also changes drastically in the soil type and the soil fertility as you go from the north to the south. So what I'm showing you here is some of the average soil test values over the last 4 years. Yorkville is in the north. I want you to notice that it has higher soil organic matter, higher CEC, and higher levels of base soil fertility. As you go in Champaign, the values are intermediate, and then as you go to the southern part of the state, lower soil fertility, lower organic matter, and lower CEC. So the research that I will show you, we have generally done at each of these sites. This allows us to have locations that differ in their soil fertility. These locations also differ in their weather. In Illinois, we mostly are rain-fed, and that's because in the northern part of the state, we have 500 millimeters of precipitation during the growing season. Down in southern Illinois, it's probably 450 millimeters of precipitation. So we can grow corn in Illinois under rain-fed conditions, usually without irrigation. So this is where we do our research. In order to control variation, we use the same research equipment at all sites. We move our research equipment between sites. And I have some very excellent research equipment designed for small plots. So the research I'll show you is done in replicated small plots. To me, a plot is typically 12 meters long, 3 meters wide. We've planted all of our trials with this equipment. Here we are ready to go to one of our outlying research sites, and it takes a lot of effort to move that equipment. You can see we have a semi-truck with our toolbar and our sprayer. We have our planter. We have our fertilizer applicators. We bring all the fertilizer, all the liquid, all of the seed. We have to bring everything we need with us when we go to a research site. We even bring this important piece of equipment because our equipment is powered by diesel fuel, but the students are powered by caffeine. And in Illinois, our caffeine is coffee. I know you would use mate in Argentina, but we bring this important piece of equipment to us. Now, speaking of our students, I have to acknowledge my research team. This is my research team of students that have done the research, 10 graduate students, 5 PhD, and 5 master's students, an excellent team. Of course, I don't have to tell you how unique 2020 was with the pandemic. We were very fortunate to be able to do our research in 2020. We had to wear masks, we had to socially distance, but the good news is this is me, and I'm a person that actually looks better when I wear a mask. I can't tell you how I'd rather be with you in person giving this presentation. I can't tell you how soon I'd like to see this pandemic end. And my thoughts and prayers are with all of you who've been affected by the pandemic, who's lost friends or loved ones. The sooner we can get over this, the better. So I'm going to try and engage you with some questions throughout my research. And my first question is, what management factors have the biggest impact on maize yield each year? This is an open-ended question, And I think a lot of you know the answer to this because this is our 7 wonders of the maize yield world. This is our concept where we rank those management factors that each year can have a positive, sometimes a negative impact on maize yield. We've worked on maize long enough that I can give each of these factors an average ton per hectare value. Of course, I want you to recognize that value is an average. It's an average of a range. Sometimes the range is fairly large, and I've done my research in Illinois in the United States. It might be a little different in Argentina. Now, before I get into the 7 wonders, I want to say that there are some crucial prerequisites. And I don't mean they're not important. They're actually crucial, but they either don't add yield or they don't need to be done every year. I can't tell you how important the soil structure is, and to have well-drained soil that can definitely add yield, but it's not something that you do every year. Weeds and pests, as important as they are not wonders because they take yield away rather than add yield. And you know how we base our soil fertility? We take a soil test. Sometimes we can adjust the pH and make nutrients more available. I'm going to view the soil test as base levels of nutrients. And I'm going to show you that it's not necessarily in today's production the only thing that we have to pay attention to. It gives us an idea of the base, but I think we have to fertilize above that base for high maize yields. So I'll assume that we have these prerequisites met, and then what are the top 7 factors that impact maize yield each year? I don't have time to go into each of one of these. I could speak about each of these for probably an hour, and I am going to highlight 2 of them, but I show them all here to you here just so you get an idea of what are the major management factors that impact maize yield. So I list them here in order of importance and their average value. Now, one thing I want to point out about these 7 factors is they all interact with each other. And as a general rule, the higher you are on the list, the more control is exerted over the wonders below you. Think about weather. Weather affects every one of these management factors. 7 factors, all of which interact with each other. This is what makes maize production so challenging and so interesting. The key to high yield is to attempt to manage those interactions. And these are the things we work on in our research. So I have the 7 factors here. I'll assume that you can optimize each of these factors. If you add up the value of each individual factor, you should be able to grow a little over 16 tons. And in Illinois, a 16-ton yield is fairly routine as long as we have each of these wonders optimized. Now, of course, if one of them is not optimized, I will guarantee you, you will grow less than 16 tons. 16 tons is a reasonable yield, but it isn't 20 tons, it isn't 30 tons. So how do we use this concept to grow more than 16 tons? Well, the first thing we have to do is we have to optimize each of these 7 wonders and their positive interactions. Remember, I told you that each of these things interact with each other, and the key is to have them work together in a positive manner. Now, I want to talk a little bit about one of the wonders specifically, and the question is, of these wonders, which one of these factors can you use multiple applications of and get multiple increases in yield? In other words, which one could you do more than once? And there's only one of the wonders that you can use multiple applications of, and that is the biologicals. Biologicals, this is sort of the next new thing in production agriculture. And what do I mean by biologicals? When I say biologicals, I'm going to put it put them into three groups. They could be the plant growth regulators. I hope you can tell from the name what plant growth regulators do. They regulate plant growth. These are things like auxins, gibberellins, cytokinins. Sometimes these products can be used to have a direct impact on plant growth. Sometimes other practices can have an indirect impact on plant growth by affecting the synthesis or the activity of a plant growth regulator. And one example of an indirect plant growth regulator effect is the leaf greening, the leaf health that often comes from a strobilurin-based foliar fungicide, even in the absence of visual leaf disease. So, we apply the fungicide around tasseling time, and then 50 days later, we see the plant is greener. Mostly the lower leaves are greener. At least that's where it's the most easiest to see. And of course, this can have a big impact on how well the crop stands and how fast you can harvest the crop. Also, since the leaves are what intercepts light and carry out photosynthesis, by keeping them active longer, we can get heavier kernels and an increase in yield, even when there isn't visual leaf disease. There's a lot of debate on what causes this, but I'm going to tell you that one of the things that strobilurin fungicides do is they act as anti-ethylene agents. Ethylene is a senescence hormone in the plant, and strobilurin fungicides then act to decrease ethylene, and they have a ethylene-induced change in the senescence trajectory of the leaf. And this is a plant growth regulator effect that can give us an increase in yield, even if we don't see visual leaf disease. By the way, the fungicides work even better if you have leaf disease, but I'm going to put that in the indirect plant growth regulator category. Now, also in the biological category are microbes and biostimulants, and I said that this was the only category that you could use multiple applications of and get multiple benefits to yield. So let's talk a little bit about how biologicals can be used. First of all, they can be put on the seed. In fact, some seed already comes with a biological seed treatment. They can also be put in furrow, particularly if you're using a liquid starter fertilizer. They can be applied foliarly. Often they're applied with a post-emergence herbicide during vegetative growth. They can be applied during the reproductive stages, again, with the fungicide or with the insecticide application. And a new way that we're going to see biologicals used in the future is on dry fertilizers. I know this is an area that Mosaic is quite interested in, using biologicals on fertilizers to improve their efficiency. Now think about each of these practices. You are adding the biological to a production practice that you are already doing. So again, if you add it foliar with herbicide or you put it in furrow, there's no additional application cost. It's what I like to call a free ride when it comes to use of the biological. And if I don't have to pay for the application cost, this makes the economics of biologicals much more attractive. Now, I want to talk mostly about the next two, the beneficial microbes and the biostimulants. And there's been an explosion of these compounds in the United States. I suspect in Argentina as well. And there's been so many compounds that the first time the U.S. government in the 2018 U.S. Farm Bill actually defined what a biostimulant is. So we have an official government definition of a biostimulant. And I quote their definition here. A biostimulant is a substance or a microorganism. Again, it can be applied to seeds, plants, the rhizosphere. It's going to stimulate processes that enhance nutrient uptake. I think that's one of the major goals of this presentation. Increase the efficiency of nutrient use and or the tolerance to stress, with the net result being better quality or higher yield. Now, I will tell you that I often talk to growers and they say to me, well, I used a biological, and they don't have any idea of what that biological did or whether it was effective or not. And they say, I used a biological, I can't tell if it worked or not. And this is a major problem that we've seen, that one needs to categorize the biologicals into groups. You have to understand what they do, where they're going to do it, in order to determine what type of biostimulant or biological compound you might need. So what we did is we took the beneficial microbes and biostimulants, and we put them into 7 different classes. So the first 3 involve microbes. Those can be bacteria or fungi. And then the next 4 involve biostimulants. And what this allows us to do is take products and put them into one of these 7 subcategories. And then if we know what that subcategory does, we can help position whether an individual grower needs or can take advantage of that product. So I'm going to talk a little bit about each one of these with you. I'm going to start with the nitrogen fixing bacteria. I think we all know that soybean takes advantage of nitrogen fixing bacteria in the nodules with the Brady rhizobium, but there are currently products that can be used on maize or wheat that also fix nitrogen. And so the goal here is to increase plant available nitrogen. And what these bacteria do is they take nitrogen gas out of the atmosphere and they convert it into a form that can be used by the plant. Now let's think about it. This represents potentially another source of nitrogen for plant growth and yield. Where does the corn plant get its nitrogen from? Gets it from fertilizer and the soil, and now there could potentially be another source from the air. And I know in the US, there's a few relatively new products that fit into this category, nitrogen fixing bacteria. There's a product called Proven N. What this is it's an edited Klebsiella bacteria that colonizes the root and continues to fix nitrogen right in the root zone. There's another bacteria, one developed from as an endophyte from sugarcane, that actually colonizes inside the plant within the leaves and the roots, and also fixes nitrogen that it slowly releases to the plant. I like to think of these as sort of the first generation of products. We've evaluated these products. We have seen that under some cases, these products can provide somewhere between 30 and 40 kilograms of nitrogen to the crop. And I know this is an area that Mosaic has an active partnership in to try and develop even better nitrogen fixing bacteria that are going to help supplement the crop's supply of nitrogen. Now, another microbe that is potentially used is what I'll call phosphorus solubilizing bacteria. And the goal here is to increase the availability of mineral phosphorus. This is phosphorus that is already in the soil. So I think you know that soil has a lot of phosphorus, which is bound. It's bound with other cations like aluminum or calcium, and when it's in bound form, it's not available. So when you add a phosphorus solubilizing bacteria, these bacteria make weak acids. These weak acids then solubilize the phosphorus away from the calcium and the aluminum, and now they make it available for plant growth. So not only can phosphorus solubilizing bacteria help improve the availability of phosphorus already in the soil, but in many cases, if they're paired with a phosphate containing fertilizer, they keep that phosphorus available to the plant. Now, the last one I'll talk about in the microbial category, and this is a fungi, and that is mycorrhizal fungi. Mycorrhizal fungi have been around for a long time, and what they do is they act as an extension of the crop's root system. So again, here we put a mycorrhizal fungi in furrow. You can see from the soil core there that these fungal mycelia, and these fungal mycelia then greatly extend the surface area of the soil that can be exploited by the plant. They're particularly important in the uptake of immobile nutrients like phosphate and like many of the micronutrients, and they also help the plant to acquire water. So 3 categories involving the living microbes that might act as different potential biostimulants. Now the next 4 categories are somewhat unique. One of them, the newest one, is what I'll call enzymes, and these are different purified phosphatase enzymes, and their goal is to increase the availability of organic phosphorus. Of course, the phosphorus solubilizing bacteria increase the availability of inorganic phosphorus, and these phosphatase enzymes are designed to act on phosphorus that is part of soil organic matter. And I have a little graphic to sort of demonstrate how they work. I mean, here we can see organic matter that contains phosphorus. We add the phosphatase enzyme. It binds on the organic matter and releases the phosphorus from that organic matter so that it is now available for plant growth. These enzymes might be important in soils that have been amended with manures. So manure amended soils has a lot of organic phosphorus, but sometimes it's just simply not released fast enough. So purified enzymes are another way to help make phosphorus available. Another one of the biostimulant categories, and this one's been around for a long time, and that's the humic or fulvic acids. I like to think of humic and fulvic acids as sort of the active ingredient of soil organic matter. If you take soil organic matter and you distill it down to its most active compounds, they're humic and fulvic acids. And I have the structure of some of these compounds here. I want you to notice that they have a lot of carboxyl groups. So they're highly negative charged, multi-polyionic carboxyl groups, and they act as natural chelates. So these compounds chelate cations. They can chelate cations. They play a big role in the chelation of iron and zinc. And by chelating those cations, it prevents them from binding with phosphorus. So they could make both phosphorus and important cations like zinc more available. Now, not only that, if you look at these compounds, they have a pretty high carbon content. And when applied in the soil in the root zone, they stimulate soil microbial activity. They're like a food source for the microbes. And if you can stimulate those microbes in the root zone, that can improve root growth and nutrient uptake. So the humic and fulvic acids have a dual role, both as chelators and as carbon sources for microbes. Now, all of these first ones that I talked about, they primarily have to be applied in the rooting zone or to the soil. The next 2, I grouped these together. The marine extracts and the sugars, they're a little more versatile in their use because they could be applied either to the soil or they can be applied foliarly to the vegetation. Now, when they're soil applied, the goal is to stimulate microbes, often as a food source for microbes. When they're foliar applied, they act as signaling molecules, often to upregulate processes that help the crop protect against stresses. And drought stress is one of their major roles. So if you look at the marine extracts, it's a pretty interesting group. By the sound of the name, they come from different marine sources. They can vary. They can come from algae, they can come from seaweed, they can come from kelp. I'm going to say the most common source of a marine extract is really a brown seaweed, Ascophyllum nodostrum. But you can also make some of these products from red or green algae. And the key thing about marine extracts is they contain multiple active biomolecules. They are a cocktail of different products. They might contain some plant hormones, amino acids, some carbohydrates, some micronutrients, a whole host of compounds that can have biostimulatory impacts on crop growth. Now, one thing that's common in many of these products is to put a little bit of fertilizers or nutrients in them. So here's a common marine bioextract, and I want you to notice it, again, it's from this brown seaweed, but it also has a little bit of soluble potassium in there. Now, I don't think that's the active ingredient. I think the major active ingredient comes from the brown seaweed and its biostimulatory capabilities, but in many cases, a little bit of mineral nutrition is added to these biostimulants, and I think that helps to call them fertilizers, where they're really acting as biostimulants. And then the last category, the sugars. So sugars, I show some of the common sugars here: glucose, fructose, monosaccharides, the disaccharides, sucrose. A lot of interest in these products as potential energy sources for soil microbes. When you put a sugar in the seed furrow, it's like giving that soil microbe an espresso shot or a dose of mate. In other words, it stimulates the microbial activity around the root zone and helps that plant then to get off to a quicker start. Now, that's when they're applied to the soil. When they're applied foliarly, they often act as signaling molecules to help in the transport of carbohydrates, or again, to help the crop tolerate stresses. So I've given you a little lesson about the categories of biologicals. I put them into 7 groups. Hopefully I've educated you that these things do different things. They're applied in different ways. And you really do need to know what they do and how they work if you're going to make a decision to use one of these products. So I'll tell you my perspective on biologicals. I'm skeptical, but I have an open mind, and I'm willing to try them and learn from it. All growers that I know that grow high maize yields, they do so partly by trial and error. They're willing to try, observe. So I'm skeptical, but I have an open mind and I'm willing to try them. But I clearly want to know what they do and how they work. Now, I know a lot of these products are going to be marketed as a replacement for fertilizers. They are not. I'm going to stress that biological products are not a replacement for good crop management. Where I see them as most effective is the progressive grower in getting us to the next yield level. So they're clearly not a replacement for good crop management. All right, well, I told you to get high maize yields, you need to optimize each of the 7 wonders, their positive interactions. I showed the value of biologicals. I said that they might have multiple applications. I mean, you could put one on the seed, you could put one on vegetatively, maybe get multiple effects. The other question I have for you, and again, this is about each of the 7 wonders, and I want to ask the question of these 7 factors, which one of these has changed the most in the United States over the last 50 years? So over the last 50, 55 years, which one of these has changed the most? Now, of course, I know hybrids and varieties have changed a lot of improvement in the potential. But I'm going to tell you the factor that's changed the most in the U.S. over the last 55 years is the plant population, the number of plants planted. So when I say plant population, I'm referring to how many plants per hectare. plant population, plant density, seeding rate, plant stand. They all mean plants per unit area. And this is the factor that's changed the most in the US over the last 50 years. I'm going to show you the average yield of maize in the US over the last 55 years, and then I'll superimpose over that the average planting population during that same time period. So what I'm showing you here is the average yield of maize in the US in tons per hectare. That's the orange triangles. I want you to see that the average yield of maize in the US, it goes up and down depending on that year's weather. These are few bad weather years, but on average, the yield of maize in the US goes up about a ton every 7 or 8 years. Now, associated with that increase in yield has been a linear increase in the number of plants planted. That's the blue line. Notice the blue line does not go up and down like yield, because you actually have to plant the plants before you know what the weather's going to do to impact the yield. But what I want you to notice, I want to go back to 1965. In 1965, the average yield of maize in the US was a little over 4 tons, planting less than 50,000 plants per hectare. And now, 55 years later, the average yield's more than doubled. And the average planting population in the US this last year was just under 79,000 plants per hectare. And it's going to go up. Despite the fact that seed's expensive, plant population has to increase in order to grow high yield. And one of the reasons the plant population is so important for high maize yield is that it is a component of maize yield. You can make maize yield into a math equation by multiplying the 3 yield components together. So the yield of maize is a product function of how many plants you have per hectare, how many kernels you have on each plant, and the weight of each individual kernel. And an increase or decrease in any one of these components can be responsible for an increase or decrease in yield. And these components act at different times in the growth and the life of the plant. Plants per hectare, that's determined at planting and emergence. Kernels per plant in the determinate maize plant, that's determined of the period around flowering. And weight per kernel is determined during seed filling. Now, the goal is to increase yield. And in order to increase yield, you have to increase at least one or more of these yield components. You can think of a way to increase yield without increasing one of these components. I'd like to know it. So you have to increase one of these. Now, sitting here in the audience today, which one of these do you have the most control over? The yield component you have the most control over is plants per hectare. I mean, you actually have to purchase and plant the seed, but plants per hectare, the plant population, that's the yield component that the grower has the most control over, and that is the reason that plant populations continue to increase. If you look at the rate of increase in the US, it increases about 900 plants per acre per hectare per year, and it's only going to go up. Now, I'm going to make a long story short without showing you the data, and I'm going to tell you that the maximum plant population that you can put in a 76 centimeter row, in the US we use 76 centimeter rows, so the maximum plant population you can put in a 76 centimeter row is about 93,000 plants per hectare. If the US is at 79,000 plants per hectare now, and if 93 is the maximum you can put in a 76 centimeter row, that means the future of maize in the US has to be narrow rows. Now, I know that in Argentina, you already are in 51 centimeter rows. In the US, we're in 76 centimeter rows. So here's something that Argentina farmers do better than US farmers. They are already in a narrow row. And there's some real advantages to a narrow row. So if you look at this particular picture, 76 centimeter rows, 51 centimeter rows, same number of plants, fairly high density, 109,000 plants per hectare. What I want you to notice is by narrowing that row, see how with the same number of plants, see how more of this ground area is covered by green. So same number of plants, narrow row, we can intercept more early light. And that's a huge advantage. I think the whole premise behind agriculture is light interception. So by narrowing rows, we intercept more light. It also allows us to manage a higher population of plants. If you have 109,000 plants in a 76 centimeter row, and they're perfectly spaced, there are 12.2 centimeters apart, too close. But when I have a 51 centimeter row, again, 109,000 plants per hectare, now they're 18 centimeters apart. This allows me to manage a higher population of plants. This has to be the future of maize production in the US in order to manage more plants. So I showed you that plant population has gone up, going to continue to go up. And then I have another question related to plant population. And the question is, what happens to the size of each plant's root system as the population of plants is increased? So as I grow more plants, what happens to the size of each individual plant's root system? Well, I hope this is an easy question. It gets smaller. So when I have more plants, each plant has a smaller root system. And I have photographic evidence to demonstrate this because digging and washing roots is my graduate students' favorite task. They love washing and digging roots. Talk about a good time. Here we are with a major root digging and washing operation. So here, notice we are collecting the roots. We're soaking them, and then we're pressure washing the roots. We're storing them here. We're going to scan them and photograph them later. There's nothing that my graduate students would rather do than dig and wash roots. This is their favorite task. I mean, just look at the picture and how much fun each of these graduate students are having washing off those roots. And so I have photographic evidence that as I increase the population of plants, each plant has a distinctly smaller root system. So again, as I go from 74,000 plants per hectare to 103,000 plants per hectare, look at what happens to the size of each plant's root system. Not only can I see it visually, but we've weighed it to quantify that change in root mass. And if you look at these weights of these root systems, for every 1,000 plant increase in population per hectare is a 1% decrease in root mass. So again, as I plant 1,000 more plants per hectare, I decrease the root mass of every plant by 1%. I just showed you that increasing plant population has to occur for high yields. And I'm going to pose a question related to fertilizer management. As I grow more plants that have smaller root systems, is this going to mean I have to change how I fertilize and manage the crop? Well, the easy answer is yes. When I have more plants with smaller root systems, I'm going to have to do a better job of fertilizing that crop. Now, I'm not sure about Argentina, but I know about the US. I know in the US, we rely heavily on the soil test. The soil test tells us what we need to add. The yield tells us what we need to replace. And I have a question for you related to soil test values. So when were soil test values calibrated to maize yields in the US? What year was that done? The soil test values were calibrated to maize yields in the US in the 1960s and the early 1970s. Again, 50 plus years ago. And we're still using the same soil test values today. Now, anything different between how we grow the crop now than how we grew the crop in the 60s and 70s? Well, one big difference is we're growing more plants. See right here where I have this red circle? That was when soil test values was calibrated to maize yield. Lower yields, fewer plants. Those fewer plants had bigger root systems. Now we're growing more plants with higher yields that have smaller root systems. I'm pretty sure this means we're going to have to do a better job of fertilizing to ensure adequate plant nutrition. How are we going to do that? This is another one. This is another question. How are we going to ensure when we plant more plants with a smaller root system that there's adequate plant nutrition for high maize yield? Well, it all comes down to the 4 R's. Put in the fertilizer in the right rate, at the right time, the right source, and the right place. Now, I want to talk a little bit about the source and the time. And I want to ask you, are all mineral nutrients absorbed by the plant in the same amounts at the same time? Are they used in the same way? I mean, are all nutrients used exactly the same? Now, the easy answer to this would be no. Mineral nutrients are absorbed different rates, different times. They have different functions in the plant. So I want to cover this with you a little bit, and I want to show you my 6 favorite nutrient elements. And what I've done with these 6 elements is I'm showing you how much of each of these 6 elements is required to produce 14.4 ton maize. So what I'm showing you here for each of these nutrients, how much of each of these elements a 14.4 ton crop has to absorb over the course of the growing season. And that has to come from fertilizer or the soil. I also show you here for each of these nutrients, how much of each of these nutrients is removed when you harvest a 14.4 ton crop. In other words, this is how much of each of these you are physically taking off your field. This is sort of analogous to removal. And then I also show you what's known as the harvest index. And the harvest index is of the amount that the crop takes up, what percentage is removed with the grain. So harvest index is the percentage of the total uptake that is removed with the grain. And the important part I want you to see is that the harvest index is different for different mineral nutrients. Now, if I have a table like this, there are 3 important criteria that I use to determine the importance of a mineral nutrient for high maize yield. So my number 3 criteria is that the nutrient element has an interesting seasonal pattern of uptake and partitioning over the course of the season. And that would be very true of the micronutrient boron. Boron has a very interesting pattern of uptake and partitioning over the course of the season. So what I'm going to do, I'm going to show you this for a number of nutrients. And so what I'm showing you here, this is for boron. I'm showing you the uptake and partitioning of boron for 14.4 ton maize. So what I have here is boron uptake, grams per hectare. It's grams because it's a micronutrient, as a function of time. And I've expressed time on thermal time, cumulative growing degree days. I've also expressed time as a function of growth stage, V for vegetative, R for reproductive. And by partitioning, I mean, where is that boron within the plant? Is it in the leaf, the stalk, the cobs, husk, tassel, or the grain? Now, I said that boron had an interesting seasonal pattern of uptake. So I can track the seasonal pattern of uptake here. That's over the course of the season. And there's an interesting component here. And that interesting component occurs right here at flowering, at VTR1. What I want you to notice at VTR1 is the plant actually loses boron. So notice that there's a temporary loss of boron from the leaves and the stem. And the reason that occurs is that boron is being lost in the pollen. Boron is very important for viable pollen and for silk growth. And at flowering, there's a loss of vegetative boron in pollen and silks at flowering. And by the way, if the crop is under stress, oh, this can be even more important. So that's an interesting seasonal pattern of uptake. Another important criteria for a mineral nutrient is that the crop needs a lot of it, and it needs to accumulate a lot of it in a short amount of time. And that would be true of the nutrients nitrogen and potassium. I know potassium is not a major macronutrient in Argentina. It is in the US. So I'll use nitrogen as my example. You'll notice that the plant needs to accumulate a lot of nitrogen. See how this is the biggest number of all. And I'm going to show you, using the uptake and partitioning pattern, that it has to accumulate it in a short amount of time. So again, I'm showing you the uptake, kilograms per hectare nitrogen, as a function of time, and where it is in the plant, and where is the period of most rapid uptake. When is the slope of this line the greatest? Well, it's greatest right there between V10 and R1. So between V10 and R1 is usually 21 days, late vegetative growth right before pollination. During that time, a 14.4 ton maize crop has to accumulate more than 8 kilograms of nitrogen every day for 21 straight days. That's a lot of nitrogen in a short amount of time. And that's because at this time, the plant is developing the leaves and the stem. Leaves are going to play a very key role in photosynthesis. This is not the time to be short of nitrogen because we're making the light interception and the photosynthetic capacity of the plant. Now, my number one criteria, and this one is by far the most important, is that the nutrient has a high harvest index value. Remember, I said harvest index is the percentage of the total plant nutrient uptake that's removed with the grain. So harvest index is the grain nutrient divided by the total plant nutrient. And my thinking is, I want a lot of grain. And therefore, those nutrients where most of what the plant takes up are removed with the grain must be the most important ones for high grain yield. In other words, I want grain, and if most of what the plant takes up ends up in the grain, must be pretty important for high grain yield. And given that, the elements that have the highest harvest index values, the ones that I believe are the most important for high maize yield, are nitrogen, phosphorus, sulfur, and zinc. I want you to notice they have the highest harvest index values of any of the mineral elements. Now, nitrogen, not only does it have a high harvest index, but it also requires a lot in a short amount of time. And it is, after all, the second wonder of the maize yield world. So I'm going to revisit the uptake pattern for nitrogen. And what I want you to see is that by the time the crop flowers, it has 75% of its nitrogen that it needs in it, but it still has to take 25% of its nitrogen up after flowering. And that's to support the developing grain. So a quarter of the uptake has to occur after flowering. Typically, that's not enough to meet the needs of the grain. So I want you to notice that nitrogen is redistributed out of the leaf and the stem in support of the grain. And this screams limiting factor, but it is, after all, the second wonder. So high harvest index, redistribution of nitrogen out of the leaves and stalk. Now, it's a little bit different for sulfur. I will tell you that sulfur plays the same physiological role in the plant, but it doesn't have the same uptake pattern. So I show the uptake pattern for sulfur. And what I want you to notice is that sulfur uptake is season long. Half of the sulfur that the crop has to take up has to occur after flowering. Half of it. Now, unlike nitrogen, that can be redistributed out of the leaf, notice that sulfur is relatively immobile in the plant. In other words, once it's in the leaf, you don't take it out of the leaf and move it to the grain. And so that means this large grain requirement for sulfur has to be met by taking sulfur out of the soil. This means that sulfur needs to be available in the root profile for the whole season. The exact same thing occurs with zinc. Here's the uptake pattern for the micronutrient zinc. Again, it's season long, half of the zinc taken up after flowering. Almost no redistribution out of the vegetative tissues. So we have to have season-long uptake of zinc. Zinc also has a harvest index of over 60%. And the exact same thing occurs for phosphorus. Notice that phosphorus uptake has to be season-long. Huge seed requirement, grain requirement for phosphorus. It has the highest harvest index of any of the elements. Almost 80% of what the plant takes up is removed with the grain. And there can be a little bit of redistribution out of the leaf and stem, but still the great bulk has to be taken up from the root. So we need nitrogen, sulfur, zinc, and phosphorus has to be available season long. So as I look at these 6 important elements for high maize yield, I had to pick my 4 favorite. My 4 favorite would be nitrogen, phosphorus, sulfur, and zinc. My idea of a better fertilizer source would be a fertilizer that has all those elements co-granulated in the same granule. And that's precisely what MicroEssentials SZ does. MicroEssentials SC is a co-granulated fertilizer that supplies nitrogen, phosphorus, sulfur, and zinc all in the same granule. So in other words, when a root comes in the vicinity of a MicroEssentials SC granule, those 4 elements are immediately available. Now, the other thing that I like about MicroEssentials is it has a component that helps keep some of those nutrients available. I think you know that the sulfur in MicroEssentials is a mixture of elemental sulfur and sulfate sulfur. That elemental sulfur slowly oxidizes. It acidifies the MicroEssentials granule, and it sort of acts like a phosphorus solubilizing bacteria. It acidifies the granule, that keeps the phosphorus available, and it provides a season-long source of sulfur. So that's one of my ideas of an innovative fertilizer source that's going to help provide the crop with 4 of the key nutrients that it needs. Now, the other thing I think we clearly need to do is we need to put the fertilizer in the right place. And the right place is where the roots are. So the right place to put any fertilizer is in the crop's rooting zone. Now, once again, why is it so important to place fertilizer in the crop's rooting zone? And I'm going to remind you of the size of the maize crop's root system. The maize crop root system only extends about 15 to 20 centimeters horizontally. So I have a picture of a maize root system here. This is at 79,000 plants per hectare near the end of the season. I have a scientific instrument here that allows us to quantify the spread of that root system. And I want you to notice, I had to do a little English metric conversion here, but I want you to notice that the root system only extends about maximum 20 inches horizontally. Roots do not cross the row. I mean, I know you see pictures of maize plants with huge root systems that are, 3 meters deep and 2 meters wide, and that's not a maize plant. That's called a tree. So maize root systems only extend about 15 to 20 centimeters. And this is at 79,000 plants per hectare. As you increase the density, their horizontal spread is even less. It's because of this that we have to do a better job of placing fertilizers. Now, I do have a couple of opportunities for better placed fertilizers. One thing you can do right off the planter is you can put a liquid fertilizer, so often called a starter fertilizer, at planting. These can be placed in the seed furrow, or you could place it 5 centimeters to the side and 5 centimeters deep. Our research planter is equipped with in-furrow capabilities. So this is our research planter. We have 3 different tanks, different hosing and pumps on the planter. This allows us to put starter fertilizer, different combination of biostimulants within that starter fertilizer, all right on the go. And what we're doing here, here's a close-up, is we're putting that liquid right in the seed furrow. So you see here, there's a biostimulant being put in. Here's a starter fertilizer being put in. The idea with the starter fertilizer is I'm going to put it right in the root zone of that developing crop. I'm going to try and get that crop off to a faster start. And many times we see improvement in growth, early growth, when we use a starter fertilizer. So you see here, compared to no starter, here's 11 gallons of 1034O, and the crop is distinctly off to a quicker start because we place that nutrient right in the seed furrow. Now, another way that you can do a better job of placing nutrients, and this is what can be done in season, and this is a relatively new technology for in-season applications that's called a Ydrop. I think it's called a Ydrop because the apparatus looks a little bit like a Y. And so here's our research Ydrop applicator. And so with this Ydrop applicator, we can place that liquid fertilizer right adjacent to the crop row. Again, I'm pretty sure that's where the root is. With this applicator, we could also put the fertilizer right down the middle of the row. Now, I want you to think, I just told you that the root system only extends about 15 inches horizontally, 15 to 20 inches horizontally. So if that's true, where would the better place be to put an in-season application of liquid fertilizer? Would you rather put it right here along the row, or would you rather put it right down the middle of the row? Just saying. Got to be better if I place it where that root system is. Now, another interesting factor with maize is the architecture of the maize plant is such that maize plants act like funnels. So the maize crop will take a couple millimeters of rain precipitation. It'll funnel it right down the stem. I think this is after a very small rain event. You can see how it's wetter right along that root zone. And so this helps move in-season applications of fertilizer into the soil profile. I don't have time to show you all of our data, but for nitrogen, we've compared placing an in-season application along the row or right down the middle of the row. And along the row is at least a half a ton better when we need that side dress application. Now, we're also beginning to experiment in-season applications of sulfur fertilizers or phosphate fertilizers. And we think this also holds a lot of promise. Finally, the last method that we use to get better placement of fertilizers is to band the fertilizer right under the future crop row. We have a research toolbar that allows us to place that fertilizer 10 to 15 centimeters deep right under the future crop row. So our equipment has a RTK. We know exactly where that fertilizer was. We banded that fertilizer. We come back. We planted right over that band, and we see an enormous improvement in the emergence and early growth of the crop. All right, this particular picture is taken in 2009. This is the first time we saw it. I couldn't believe it because this is a soil test that had a soil phosphate value of 45 parts per million. So the soil test says plenty of phosphate, plenty of sulfur, plenty of zinc. But when we banded that MicroEssentials SZ right under the crop row, we saw an enormous improvement in the early growth. And I've seen this 100 times, almost every single time, regardless of the soil test. Now, if I look at this row here that doesn't have the banded fertilizer, I see what is one of the biggest problems that I think limits crop productivity, and that's what I call a plant left behind. See this plant right here? This is broadcast fertilizer based on soil tests, only 79,000 plants per hectare. This plant emerged 2 days after its neighbors, and it's behind. Now, a lot of things cause that. That could be the seed, it could be the depth of the seed, it could be the speed of the planting. So a lot of things can cause that plant to be left behind, cold soil temperatures. But one thing I do know is this plant will never catch up to its neighbors. And if it turns off dry, this plant is like a weed. And I will guarantee you that this plant has a smaller ear. But when we ban that fertilizer, in this case, 280 kilograms of MicroEssentials SC, right under the crop row, even with more plants, 109,000 plants per hectare, not only do we have less plants left behind, but the plants grow faster. So this is the same hybrid, planted the same day, the picture taken the same day. The difference is, on this side, I banded that fertilizer right under the crop row. I even have more plants, and they're bigger, and there's less plants behind. Young maize plants sense their fertility at an early age, and it sets the growth potential. The growth potential and the yield potential of maize is set early. The plant senses it. Now, I won't guarantee that this gives a higher yield, but it sure sets the possibility for higher yield. Now, let me ask you, if we banded that fertilizer under the plant, to get that plant off to a greater start, if I have adequate fertility under the plant, does that allow me then to put together a system, a systems approach where management factors are going to work together to improve yield? So this is the last thing I'm going to cover with you, and I'm going to show you some of our systems approach to combined management factors to increase maize yield. And what I'm going to do is I'm going to compare 6 years worth of research. I think it's 16 different trials where we compared a standard grower practice to what we call an enhanced management system. Now, in the standard package, we used our fertility. We use P and K. We use K. You might use sulfur, but it was based on a soil test. We applied what the soil test told us, broadcast. We used 180 kilograms of nitrogen, pre-plant, 79,000 plants per hectare, no fungicide, 76 centimeter rows. This would be a sort of a standard agronomic practice in the U.S., provided the soil test was high enough. We compared that to the enhanced system. So in the enhanced system, regardless of the soil test, we fertilized to provide my 6 favorite nutrients. We banded MicroEssentials SZ to provide phosphorus, some nitrogen, sulfur, and zinc. I show you the amounts here, and we're shooting for 20-ton maize, so that's what the amounts are based on. And then we used another mosaic product, one I don't think you use that much, but it's pretty important in the U.S., and that's called Aspire. And that's potash that also has boron as part of the granule. And by supplying those 2 fertilizer sources, I can get my 6 favorite mineral elements that are necessary to grow 20-ton maize. We used 180 kilograms of nitrogen pre-plant, just like in the standard, but then we put another 80 total as a side dress, 260 kilograms of total nitrogen. Recently, we've been using the Ydrop to make that side dress application, get it right along the crop row. We upped the density, the population to 109,000 plants per hectare. We put a fungicide on at flowering, a strobilurine-based fungicide, and then we narrowed the row spacing to 51 centimeters. So our enhanced system compared to the standard. Now, I will tell you, we can see this in the field right to the crop row. So I have an example here. Here's what the crop looked like, standard management. Here's what the crop looked like with enhanced management. And the standard management looks pretty good. but that's because we don't have this enhanced one right next to it. I mean, you tell me which crop looks better and which crop you think has the higher yield potential. Very visual early season difference. We also see a late season difference. We see a late season difference on the health of the crop. Notice how the crop is greener, especially on the lower portion of the canopy. We have more ears since we planted more plants. And in many cases, we have larger ears. So what I'm going to do is I'm going to show you the difference in yield between the enhanced and the standard system. I'll break it out over each of the 6 years. And again, I'll average it over the trials at each of the locations. I mean, it is true that sometimes at a given location in a given year, things can be different. But when you average it over the trials, so I've averaged it over the trials. This represents 16 different site years. What I'm showing you here is this is the standard yield. This is the enhanced yield. And this triangle is a scientific symbol that means I subtracted the standard from the enhanced. And what I want you to see is on average, that enhanced yielded 3.2 tons more than the standard. I mean, the value of the enhanced differs according to the year. Some years are better than others, but on average, over 3 ton increase in yield from the enhanced. Now, I also want you to notice, and this is especially true if you look at the enhanced. If you look at the yields over the 6 years that we got with the enhanced management, notice that each year the yield is higher. And this is because each year we're using the next best hybrid. The genetic potential of the hybrids changes so fast. Each year, as we take the next best hybrid and we manage it, see how the yield potential continues to go up as long as we manage it. Now, here's a key question. I have 5 factors worth 3.2 tons. Is each of these factors worth 0.6 ton, or are some of the factors worth more than the other? I have 5 factors. I like to think of this as my basketball team of management. Which factor is the most valuable player? That is a very difficult question to answer statistically. So to answer the question, which factor or factors has the biggest impact, we use what we call an omission addition experimental plot design. This is an unbalanced factorial, 12 treatments. What we can do with this particular design is we have the enhanced system in blue that has all 5 factors. We have the standard system in orange, that's none of the enhanced factors. I like to think of this as like 2 different basketball teams. So the blue is the professional team, the orange is the amateur team. I'll assume the professional team is better than the amateur team. And then what I do, one player or one factor at a time, is I replace the professional player with an amateur player, and I see how much that one amateur factor impacts the performance of the other 4 pro factors. That's why it's called an omission plot. What would be the loss in yield if I omitted one of the factors? And notice we do that for all 5 of the factors. Now on the other side, to the standard practice, I take one professional or pro factor and I put it on the amateur team, and I see how well one enhanced factor can elevate the performance of the other standard factors. This would be like if you had 5 side-by-side individual comparisons. Now I can tell you, if you visit my research plots, this makes a great visual demonstration in the field, because you can look at these plots and you can see a huge difference in the appearance and the yield of the crop in a small area. So what I'm going to do first is I'm going to show you what would the value be if you added just one of these factors. So if you added one factor and only one factor, what would the impact on yield be? And again, I'm going to average it over all of the trials just because in the interest of time, it makes it easier to see. So I've averaged it over all 16 trials. I'm showing you the standard management, a yield of 13.4 tons. And now I'm looking at the impact of adding one factor, only one, on yield. So by the way, the biggest factor, the factor that had the biggest impact on yield was the fertility. When I added to my 6 favorite elements, I want you to notice that I got almost a ton increase in yield over the standard. This pretty well tells me that we're not doing a very good job of fertilizing the yield potential of today's hybrids. When I put that extra 67 kilograms of nitrogen on, 0.6 tons. Now, it's not that side dress nitrogen is not important. It's that the need for side dress nitrogen is heavily influenced by the weather. If I have weather years with a lot of spring precipitation, that side dress nitrogen is very important. So the range in this factor is quite large depending on the weather. If I run the population up to 109,000 plants per hectare, that's all I do. Notice I lose yield. You cannot increase the population without managing it. When I put the fungicide on, again, the fungicide is one that's heavily influenced by the environment, partly because the environment influences the degree of disease. The fungicide's worth 0.4 ton. And when I narrow the row spacing from 76 centimeters to 51, I gain 0.6 tons. So at least 4 of these are in the right direction. Population's not. Now, if I said, well, I'm going to use all 5, and I'm going to estimate the value of all 5 based on their individual value. So if I summed up the individual value of each of these to try to predict what the value of using all 5 would be, I would add all these, I'd have to subtract this. Based on their individual value, I would predict they're worth 2.3 tons. But I just got done showing you that the value is 3.2 tons. And this shows you that they do work together as a team synergistically, because the value of using all 5 is greater than the summation of the individual values. All right, now I'm going to show you what happens on the high-tech side, the enhanced side. So what happens on this side if I omit one factor? I keep the other 4, but I omit 1. So on the high-tech side, it's 16.6 tons, 3.2 higher than the standard. And now I want you to notice that if I omit one factor, this is omitting that factor, every factor that I omit decreases yield. Everyone. In some cases, pretty high. Notice if I omitted the extra fertility, I relied only on the soil test, I lost 1.3 tons. If I only had 79,000 plants per hectare, the ears look great. There's not enough plants. So I lose 1.2 tons. Plant population is the factor that goes both ways. If I have 76 centimeter rows, again, with 109,000 plants per hectare, well fed, those plants are too close, I lose 1.3 tons. Notice how it's not what I do, it's what I don't do that makes a huge impact on yield. Omitting any one of these factors has a large negative impact on yield. So I summarized these here just to show you the fact that in some cases, the cost of omitting the factor is greater than the gain of adding it to the standard. That would be true of the fertility, very true of the population, and also true of the row spacing. The value of those is way greater when they're combined together. In some cases, like side dress nitrogen or fungicide, the value of adding it alone in the standard is roughly the same as omitting it from the enhanced. And that's because the need for those is heavily influenced by that year's weather. If you look carefully at which factors have the biggest impact on the enhanced system, fertility, higher population, narrower rows. High yield is all about managing more plants, narrowing the row spacing, making sure you have adequate fertility. So I'm going to conclude here before I take some questions. I've roughly gone over the 7 wonders with you, not as much as I could, but I hope if by showing you those factors, those individual factors, and you understanding those that have the biggest impact on yield each year, that allows you to know what to focus on to improve your crop management. I've told you that we're going to have to grow more plants. Higher plant populations are essential, but the plant has a smaller root system. So this means we're going to have to do a better job of placing fertilizers. Banding that fertilizer right under the row, especially with the right source that supplies phosphorus, sulfur, and zinc, that sets the growth and yield potential for higher yields. I've shown you when I combine them into a system that they do work together to increase yield. And in very simple terms, the real key to higher yields is feeding, protecting, and managing more plants. Better job of fertilizing, that may or may not involve a biological. Making sure the plant's not stressed as best you're able, that may involve a biological. Managing a higher density, that could involve more plants, narrower rows. That's what I see as the simple solution to higher yield. So once again, I have to thank my students. I couldn't do the work without these students. I'm very blessed to have a group of excellent students and technicians. I want to thank the farm collaborators where I do my research. I use University of Illinois land at Champaign, but I rent land or farmers donate land to me at the outlying sites. I could not do the work without that. And then finally, I want to thank the companies that have supported my research. These are companies that supported my research in 2021. So these companies have given me product, seed, machinery, fertilizer, money, well, better yet, all of them. And I have a special shout out to Mosaic. Mosaic's been a very important and consistent supporter of my research, so I couldn't do it without it. So I have a very special thanks to Mosaic, to Bunge, to ACA. I think they're sponsoring this meeting today. I'm grateful for you to attending. I'm looking forward to answering your questions. I really hope I taught you something or at least got you thinking about ways to improve maize yield. I list my laboratory website here. At least some of this information is on the laboratory website. I wish it was all on there. But I am honored for the opportunity to speak with you today, and I'm looking forward to addressing your comments and questions. So thank you very much for your attention.